All right, babes, last video we're going to do here for section 5 is going to be focusing on what's called the kinematic equations. So the kinematic equations are a mathematical approach to solve problems of one-dimensional motion. And what they are is a set of 4 equations that allow you to solve for the variables of motion that we've been analyzing. So variable motions that we've been talking about is, one, we have distance versus displacement. Really the same kind of thing here. Again, the only difference between them would be direction, but you have distance and displacement. You have V, which stands for your speed or velocity when we take into consideration direction. You have your acceleration when things are speeding up and slowing down. And lastly, you have time, because anytime you move, there has to be some time that occurs. So each of these equations allows you to solve for some of these variables given some of the other ones. So for example, this first equation is what's known as the distance equation. It says D equals. So it's a formula given certain other variables that allows us to solve for the distance. You'll notice in here it says VI and T. So VI would stand for the initial speed, I for initial, and time, plus 1/2 AT squared. A is the acceleration, T squared is time. Notice this last chunk of this equation, 1/2 AT squared. Well, it's very similar to what we learned in section 4 with the height equation. 1/2, whoopsie daisies, 1/2 GT squared. Okay, I didn't get that equation from nowhere, folks. It actually comes from one of the kinematic equations. All right, second equation below, this equation does not solve for distance, but this solves for speed. So this is an equation that is used to solve for how fast an object is going, given its initial speed, the acceleration, that's how much speed it's gaining or losing, and the time frame, okay? Then we also have an equation over here. Now this equation is kind of a special one because it has both speed, distance, acceleration, but notice in these first 2 equations, the one variable that's common is time. So this third equation is in there because it allows you to solve for speed, distance, or acceleration if you don't know the time frame of the motion. And then the last equation, you have distance, you have your speed values and time, but hopefully you recognize here that the acceleration is missing. So this equation is useful if you don't necessarily know the acceleration. So our goal for today is we're going to talk about how to use these equations to analyze problems pertaining to one-dimensional motion. So it's going to be a little bit mathy here. It's going to be like solving word problems. As we solve these, okay, sometimes folks get confused. Sometimes these problems we can try and think through, but sometimes they get a little bit difficult. So here's kind of a way that I like to use to try and solve these problems. I call this the guess method, G-U-E-S-S, guess. First thing you should do when you read these problems is to figure out what are the given values to you. So what am I given? Am I given distance? Am I given speeds, acceleration, and time? What are the things that they are giving me? What is unknown? Now, unknowns could be things that are not given to me, things I literally don't know, but this could also be something that I'm trying to solve for. Does it ask me, for example, does it say how far? Does it say how fast? Does it say how long? That's not how, that's a W. But does it say how long, right? Does it ask those questions that then, even though it's not giving me something, I know when it says how far, that's distance, speed, and time. Then, once I know what I'm given and what I'm missing, I can then choose the appropriate equation from what I had before, one of those formulas. I plug in the things, and then afterwards I solve using tricks of math. Now, the solving part, put a little star here, this is where the algebra is going to come into play. So those of you that aren't the biggest fan of maybe algebra, yeah, you're going to have to solve equations. So it's going back to Algebra 1 and possibly Algebra 2. Shouldn't be too crazy, though. All right, so let's take a look at our first problem here. So I have I'm a hurrying. Get it? I'm a hurrying is approaching a stoplight, moving with a velocity of positive 30 meters per second. Okay? It says the light turns yellow and Amma applies the brakes and skids to a stop. It says if Amma's acceleration is negative 8 meters per second squared. Now, meters per second squared, folks, know that I give this to you guys a little bit differently. Meters per second squared is technically, I'll write it up here, meters per second. Same thing, okay? says determine the displacement of the car during the skidding process. So I want to know through this problem, it says in the end, I'll start here, determine the displacement. So that means, and I'll write this below, I want to solve for the displacement, say D. Now what I'm going to do first is I'm going to figure out what's given to me. Okay, so I'm going to highlight these. Starts off, it says is moving with a velocity of 30 meters per second. So that means my speed is 30 meters per second. Now if you go back to the equations, you'll notice I label it VI and sometimes VF. This is technically the initial speed. So I'm going to label that with an I, a little subscript, because that's how fast it's going to start. Then it skids to a stop. Now, skidding to a stop is not technically a number, but think about this. When something comes to a stop, you'll see it in the diagram here, that technically means my speed at the end is 0 meters per second. To be at rest or to come to a stop means you're not moving, which means you have a speed of 0. And then you are given the acceleration. Literally tells you acceleration is -8 meters per second per second. So I also know my acceleration of -8 meters per second per second. So my goal is to solve for displacement. I know the two speeds and the acceleration. Notice the one thing I did not give you guys is time. Okay, so there's two things. I'm not asking you to solve for time, so I don't have to solve for time. So time is one of those unknowns. It is not a given value. So I have two options. I can solve for time and then figure out the displacement, or can I solve for displacement without having time? And that's where understanding the equations is helpful because, and I'll write this down, there is the equation, the third one, VF squared equals VI squared plus 2AD. This equation has all the pieces. Heck, it even has distance in there, displacement, I'm sorry. It has VF, which I know is 0. It has VI, which I know is 30. It has A, which I know is -8. It doesn't have displacement in there, but here's the thing. I want D to be in there because I have to solve for it. I need an unknown. I can't pick an equation that doesn't have D because then I'm not solving for what I want. But this is good because if I plug my things in, so 0 squared equals 30 squared plus 2. AD means I'm multiplying, so -8 times D. I'll just leave D in there. Again, this is the thing I'm solving for. I don't know what it is. In math, we'd write that as an X. What, an X? You betcha. So now I can solve for D. How do I do that? Well, I'm going to start off first by simplifying. Okay? I know 0 squared is 0. I know 30 squared. Well, maybe some of you don't know what 30 squared is. Hey, it should give you 900. Plus 2 times -8, that's -16. And then D. I'm going to leave D in there. Notice it's becoming a simpler equation. So now I got to solve for D. Now notice D is on the right side of this equation. Okay? So to solve this, think of your solving equations tricks. I need to get D by itself, so I'm going to do inverse operations, so subtract 900 to the other side. I then have -16D left over. I will then divide by -16 to both sides. This is going to cancel. And then lastly, by dividing 900 and 16, both of them being negative, it's going to give me my distance. So I should get here 56.25. Now because they are both negative, the negative will cancel, leaving me with a positive distance. Now that positive, displacement simply means that in this case, I'm moving to the right. And you can see that in a diagram, the object is going to the right, so the positive displacement means it's just moving to the right. A lot involved. I went through a little bit more detail here, but now the next couple problems are going to go a little bit quicker. All right, so Ben Russian. Hey, what the heck? Ben Russian is waiting at a stoplight, then finally turns green. Ben accelerated from rest at a rate of 6 meters per second squared. Again, 6 meters per second squared. Think of that as meters per second, okay? For a time of 4.10 seconds, says determine the displacement. So I'm going to find displacement again. So we'll go through what do I know? So what's given to me? So it says it's waiting at a stoplight. So it says it accelerates from rest. So from rest means my initial speed, again, is going to be 0 meters per second. At a rate of 6 meters per second. Now, don't get confused here. That means my acceleration is 6 meters per second per second. And then it has a time of 4.10 seconds. And I want to know what is the displacement. So again, like the last problem, I'm solving for displacement. So what am I not given? Well, I'm not given the final velocity, and that's about it. Okay, compared to the last problem, I don't know the final velocity. I do know time, I do know acceleration and the initial speed. So I want to solve for displacement, but I don't have the final velocity, so I need to figure out which equation allows me to do that, and that would be this equation, VIT plus 1/2 AT squared. I'm going to plug in my values. Then I'm going to simplify. 0 times 4.10, that is going to cross out. Then I have half of 6. Half of 6 is going to be 3 times 4.10 squared. So what I'm going to do next is I'm going to figure out what is 4.10 squared. That's going to give me 3 times 16.81. And then lastly, I just got to multiply that number by 3, and that'll give me my final displacement of 50.43, whoopsies, 43 meters. Okay, so there we go. I solved using a different equation, and again, my equation was dependent upon what I was given and what I'm trying to solve for. All right, last two examples, babes. We're going to do some free fall motion using the kinematic equations. So in example 3, we have Luke out below. Get it? Luke out below. Ha! Drops a pile of roofing shingles from the top of a roof located 8.52 meters above the ground. And I want to know what is the time required for the shingles to reach the ground. So again, first thing, looking at the given, we are given the initial height, 8.52 meters above the ground. And lastly, you are asked to find the time. So, okay, writing this out, we are given the distance, which is 8.52 meters. Our goal is to solve for time. Ooh. Now, looking at that, we're not really given much else. Think of the other variables we had. We had our initial speed, final speed, and acceleration. And in the problem, those aren't explicitly told to us. Now, couple things. First, very similar to like when you hear being at rest or coming to a stop, notice Look Out Below drops a pile of shingles. Now, when you drop something, it's kind of shown here in the diagram, sometimes when you drop things and let them fall to the ground, you're not throwing them towards the ground, just dropping them. They're starting technically from rest. So even though it's not told to you, we know that in this case, our initial speed should be 0 meters per second. Now, the final speed would be the speed of the roofing shingles right before it hits the ground. In this case, that's not explicitly told to us. And then the last nugget is the acceleration. And this is the connection we have to make with what we learned about free fall motion, is that anytime something undergoes free fall motion, it's always going to accelerate at a constant rate. That the acceleration of any falling object, whether it's falling straight to the ground or thrown up in the air, is the acceleration due to gravity, 10 meters per second per second. So therefore, I know my acceleration is that g value of 10 meters per second per second. Now, our goal for this is obviously to solve for the time it takes to reach the ground. So in terms of our equation, we have to solve for time without knowing the final speed. So in terms of our equations, again, there's 4 of them to choose from. We're trying to solve for time. So time needs to be a part of the equation, but final speed cannot be a part of that equation because we don't know what it is. So again, we can either solve for final speed or use an equation that doesn't have it. So the equation, whoopsies, I'm going to use is that distance equation, VIT plus 1/2 AT squared. Now plugging things in, I know the distance is 8.52. My initial speed is 0. Time I don't know, plus 1/2, I know the acceleration is 10, and then times t squared. Now, looking at this, 0 times t in this first team, I have a t here and a t here, but 0 times t, that's 0, that cancels out. So what I'm left with is 8.52 is equal to 1/2 times 10 times t squared. And just to bring this up, what I have right here is that height equation that I gave you guys in the free fall motion video lesson. So in here, I'm just trying to solve for time. So the first thing I'm going to do is do half of 10. So again, I get 8.52 equals 5t squared. I would then have to divide both sides by 5 to get t squared equals 1.704. Now again, to solve for t, the last thing is I'm going to have to take the square root of both sides to get t by itself. That's going to cancel there. And then lastly, I should get t equals approximately 2.9 seconds. That's a little bit rounded, but 2.9 seconds would be the time it takes for those shingles to hit the ground. All right, last example here. Instead of dropping it, we're going to look at when things are thrown up into the air. Here I have my man Rex Things. He's throwing his mother's crystal vase vertically up in the air because, again, he likes to Rex things with an initial velocity of 26.2 meters per second. And I want to know what is the height the vase will rise from its original height. So again, it shows here in the picture, I'm trying to find the original speed. What am I given? I know I'm given the initial velocity of 26.2 meters per second. And my goal here is to determine the height. Now height, again, we can think about how to solve this. We can use our equation from section 4 on our free fall motion. But just to think about the height, technically is referring to the distance. So my goal is to solve for the distance here. I know my initial speed. Sorry, I put an F. I know my initial speed is 26.2 meters per second. Now, think about the rest of the variables. I have my final speed, my acceleration, my time. So my goal is to solve for distance, and right now, doesn't explicitly tell me what the final velocity is, the acceleration, and time. Think about our last problem. The one thing I should know right away is that my acceleration is also equal to gravity. Okay, because whether it's being dropped or thrown up the air, once you're throwing something and you just let it fly, that is free fall motion going under the effects of gravity. So I know it's going to accelerate at that rate of 10 meters per second each second. Now, sassy thing here, and this is something that we can think about in terms of just the general problem, general idea of free fall motion. How do I know the final velocity and the time? So final velocity, if I understand free fall motion, I should know that when it reaches its maximum height, as it's thrown up into the air, reaches that maximum height, we talked about that as it goes up in the air, it's going to lose speed till at this very maximum height, its final speed should be 0, comes to a brief stop. So at its maximum height, I should know its final velocity to be 0 meters per second. Another thing we talked about is time. Even though I don't explicitly tell you what the time is in this problem, we do know that every second, based on this number right here, every second it's going to lose 10 meters per second of speed. So if it starts off with 26.2 meters per second, if I just simply divide this number by 10, I know it's going to take 2.62 seconds to get to that maximum height. So I literally give you the initial speed, and using the idea of gravity and just my general knowledge of free fall motion, I now have all the variables, so I can easily solve for distance by choosing any of my equations. Okay, well I shouldn't say any, but there's 3 equations I can choose from. So the one I'm going to use is the one that actually solves for distance, so VIT plus 1/2 AT squared. Plugging in my values, I know my initial speed is 26.2, so it's not going to cancel it like last time. The time is 2.62, and then it's 1/2 of 10 times my t squared, 2.62 squared. So this one's a little bit longer, a little bit more involved. Now there is one little nugget in this problem that I did not mention in the last problem that's important for this one. In the last problem, we had an object that was falling to the ground. And when an object is falling to the ground, it's experiencing a gravitational pull that's down towards the ground. Now directionally, that means its speed and gravity are both downwards, which are technically negative directions. Now the pickle about this one is we're throwing the object up into the air, okay? Which means it has a positive speed, but its gravitational pull is always going to be directed downwards. So that gravitational pull is going to be negative. So I kind of neglected to talk about that in the last problem, but in this problem, I need to make sure that I make that value of 10 a negative 10. Okay, and that is important when we look at the direction here. Okay, now to solve this, what I'm going to need to do is simplify the right side of this equation. I have two terms, so I'm going to multiply those two numbers together, and then I can multiply this entire term together as well. So the first term, 26.2 times 2.62, that's going to give you 68.644, so we're going to round that. The second term, we have a couple things going on. We have half of 10. Now all these are going to be multiplied together, but I have the half of 10, which is 5. I have to square 2.62. I'm not squaring everything, just that number, and then I would multiply. So it's going to be 5 times 2.62 squared. If you simplify that, you're going to get 34.3. Okay? Now, because that 10, remember that 10 is supposed to be negative, I'm going to slap a negative sign in between those things. Okay? So my distance is going to be essentially the difference between 68.6 and 34.3, and we should get a distance of 34.3 meters. Fantastic. Now the difference is if I didn't make that acceleration a negative, by adding there, I'm going to get an obscene distance for throwing that vase. 34.3 meters is already impressive for Rex things. Okay? But if you was to throw it over 90 meters, actually over 100 meters into the air, dang, that's impressive. Okay, now I know Rex Things likes to Rex things, but he probably can't throw that far. You know what I'm saying? All right, babes. If you got any questions on this stuff, a lot of meat and potatoes, a little mathy, so write those things down. Email me if you need. Otherwise, we'll see you next time. Good luck and peace out.